virtuosic Chopin etude spans the entire range of the piano, from the powerful low octaves in the left hand to the expansive, uninterrupted arpeggios in the right. The sheer spread of the notes in this etude lends it its majesty. In this video, we will talk about how to measure statistical spread using a measure called the variance. We've already talked about the expected value, which measures the center of a distribution. But the center only tells part of the story. We also need to summarize the spread of a distribution. Two closely related measures of the spread are the variance and the standard deviation. In this video, we'll focus on just the variance. To understand variance, suppose we observe a random variable x. And let's suppose x happens to equal 3, highlighted in red here. We can calculate how far x deviates from the expected value, deviates from the center of the distribution, and then square this deviation. So if x equals 3, this squared deviation equals 2.56. But x is random, so x might equal, for example, 0. If x equals 0, then this squared deviation equals 1.96. In general, the larger the squared deviation is, the further x is from the center. And because we don't know in advance what x will be, this squared deviation is a random variable. Now, how can we use this random variable to obtain a single number summary of how spread out this distribution is? Well, we can look at how large this squared deviation is on average. In other words, we can take its expected value. And since this is just the expected value of a random variable, this will end up being a single number. And we call that number the variance of the random variable x, and we notate it this way. Next, let's talk about how to calculate the variance. Since we need the expected value of some function of x, the variance can be calculated using lotus. So if x is a discrete random variable, the formula looks like this, where we weight these squared deviations from the center by the PMF. If x is a continuous random variable, then the sum becomes an integral and the PMF becomes a PDF. Now, if you actually expand this square and simplify, you'll see that this formula for the variance actually simplifies to the following: the expected value of the square of the random variable minus the square of the expected value. This second term is easy to calculate. You just calculate the expected value and then square the result. For the first term, you have to use lotus again. But this lotus is easier than this lotus because you just have to weight the values of x squared instead of x minus the expected value squared. So this form of the variance formula is often more convenient for calculations. By the way, this formula for the variance should remind you that the expected value of the square is not the same as a square of the expected value. If that were true, then the variance would always equal 0, which would be nonsense. Remember that you are not allowed to interchange functions and expected values arbitrarily. If you want to calculate the expected value of some function of x, you must use lotus. Finally, let's talk about some properties of variance. First, let's look at what happens to the variance when you multiply a random variable by some constant a. If a is greater than 1, then that should increase the spread of the distribution, so we know the variance should increase. But by what factor? Let's do the calculation to find out. By definition, the variance is equal to the expected value of the square deviation of the random variable from its mean. So ax minus the expected value of ax all squared. We know that a times x is one of those special functions where you can apply the function and the expected value in any order you like. So we can pull the constant a outside the expected value. Now, both terms inside this square have an a, so I can factor out an a squared. But now this is just the expected value of a constant a squared times this random variable, so again I can pull out this constant from the expected value. Now what I have left inside the expected value is just the variance of the random variable x that I started with. So we see that the variance of a times x is a squared times the variance of x. The variance changes by a factor of a squared when the random variable is multiplied by a. What if we instead add a constant to a random variable? Intuitively, that just shifts the whole distribution over without changing the spread. So the variance should not change. Let's see how the math works out. Again, I'm going to write out the definition of variance. It's the expected square deviation of the random variable, which is x plus b in this case, from its mean. But x plus b is another one of those special functions where you can apply the function and the expected value in any order. So I can pull out that plus b from the expected value. So the expected value of x plus b is just the expected value of x plus b. I need to be careful and group the resulting two terms in parentheses. That will remind me that I have to distribute this negative sign. Now I have a plus b, and when I distribute this negative sign, a minus b, and they cancel each other out, which leaves me with just the expected value of x minus e of x all squared, which is just the definition of the variance of the random variable x that I started with. So we see that the variance does not change when you add a constant b to a random variable.